Thank you, Paula. So, as stated by Paula, in the next 10 to 15 minutes, I'm going to talk about EPSim, which is a simulator that enables you to co-simulate your control algorithms and your embedded platform in one and the same environment, and in early stages of the design process as well. And as such, we state that it enables you to do virtual hardware-in-the-loop simulation. Let me start by a small example, a scheduling example. So consider that you have an embedded platform shown here on the right, and that the embedded platform runs in a real-time operating system with a fixed priority preemptive scheduler, and 3 tasks needs to be scheduled. The first task has a priority of 4, a period of 10 milliseconds, and execution time of 4 microseconds. The second task has a priority of 5, same period, and execution time of 5 microseconds, and the third task has a priority of 6, same period again of 10 milliseconds, and execution time of 22 microseconds. My question is, how is it scheduled? Since you're in a live meeting, I'm going to provide you the answer, which is the following. The first task will be scheduled immediately, so its response time will be the same as its execution time, which is 4 microseconds. The second task has to wait a little bit before the first task has completed, so its response time will be 9 microseconds, which is a sum of 4 microseconds from the first task and 5 microseconds of execution time of the second task. And the third task, well, you can figure it out by yourself. Its response time will be 31 microseconds because it has to wait for the first and the second task. Why do I show you this example? To clearly state the difference between execution time and response time. So typically, if you're designing a control algorithm of a mechatronic system, you will start in Simulink by modeling your control algorithm. You will then generate code out of that. And of course, you want to know how much time your target platform will need to execute that code. So you will deploy it bare metal on your target platform, and you will measure its execution time. Of course, if your mechatronic system consists of multiple control algorithms, shown over here, so we have n control algorithms, and that they need to be run or scheduled on the same processor, then, as stated before, you will cluster them in several tasks that needs to be scheduled by your operating system, and as such, your response times might be higher than your execution time, as shown in the example. And why are these response times relevant? Well, I show you this because often if you're designing your control algorithm, for example, in Simulink, you're ignoring those response times in early stages of the design process. So if you have designed your control algorithm in Simulink and you push the simulate button, then your system will be solved, but in the same time, so at the same one and the same time stamp, your inputs will be sampled, your subsystem will be solved, and your outputs will be set in Simulink. But in reality, if your control algorithm runs on your embedded platform, that will not be the case, because between sampling your inputs and solving your system and setting your outputs, there will be some time, which is called response time. And this is typically not included when you're designing your control algorithms in Simulink. And EPSim tries to solve that problem by including those response time when you're designing your control algorithms. So let me tell you a bit more about the what, the why, and the how of EPSim. So to clearly state why we developed EPSim, I'll show you this slide. So if you, again, I'm repeating myself, but to clearly state that if you're designing your control algorithm, in Simulink, you connect that typically to a plant model, perhaps you have a feedback loop, and you simulate your behavior in Simulink and everything looks okay. But if you deploy that and you include your distributed platform, your software components of your control application will probably be deployed in a distributed way. You have some time delays due to the network, and of course your behavior might differ from your simulated behavior in Simulink. And this is what EPSim tries to avoid by including this embedded platform in the design, so that you can evaluate the deployed behavior in early stages of the design process. And how do we do that? Well, EPSim, depicted here as a cloud in the middle of the slide, requires some input to do that. The first input is an architectural overview of the platform. So that includes the processors that are used in your target platform, some kind of network that is included in your platform. So it needs that as an input. It also needs your software application or your control algorithm as an input. It needs some timing information of those components that will be executed by your platform. And as an output, EPSim allows you to connect those software components to or allocate those software components to your embedded platform, and to show you the real deployed behavior in the simulated environment. But what is EPSim exactly? So that cloud in my previous slide represents a library of different models that EPSim provides to you. So EPSim provides you models of tasks, interrupts, processors, schedulers like a fixed priority preemptive scheduler, but also communication models, communication medium models like SPI buses, CAN buses, USART models. That's all included in EPSim, and also some input-output peripherals like an EDC and a DEC are included in EPSim. Those libraries you can use to model your embedded platform. What can you do with EPSim? Well, as already stated, you can evaluate your deployed behavior in early stages of the design process. You can explore different deployment strategies. So you can evaluate, if you have a control application with software component 1 and software component 2, you can evaluate what the response times are in different scenarios. Let's say software component 1 has in first case a priority of 1 and software component 2 with a priority of 2. You can evaluate this behavior with the behavior where you switch to the priorities. And you can also evaluate the impact of timing delays, which might be introduced by your network, as stated in this slide. So what's in it for the industry? So in the CSE ICON project, which is currently running, we are at this moment evaluating EPSim with some of the companies that are involved in the project, and one of those companies is Van der Wiele. And Van der Wiele, they are designing and selling loom weaving machines, as shown over here on the left. And during the loom cycle, which is 360 degrees, in a certain point in time, the weft yarn needs to be cut by a scissors. And in the Van der Wiele case, that needs to be at exactly 20 degrees in the loom cycle. Of course, the scissors that are used to cut that weft yarn are activated by some electronics. And the electronics consists of an embedded platform, which is a distributed embedded platform with 2 ECUs connected by a CAN bus. And the scissors itself is actuated by a black box device, which is connected to the embedded platform by a second CAN bus. The black box device, of course, actuates the scissors at a certain point in time in the loom cycle. Of course, the electronics introduces some delays. So the first category of delays are the sensor delays. So it needs some time for the sensor to get to your algorithm. Algorithm calculates when exactly the scissors needs to be activated, and of course there's also the delay of the actuation, which includes the second CAN bus and of course the black box device. So what can EPSim do in this case study? So EPSim will try to figure out at which point in time the send command needs to be, the cut command needs to be sent. EPSim tries to determine the exact point in time in the loom cycle at which the cut command needs to be sent. So how do we do this? Well, the electronics are modeled using EPSim. So EPSim provides some libraries to do so. So the platforms are modeled in this way. So we have a model of their ECUs, which includes the certain scheduler, also the tasks that are running on the embedded platforms are modeled. The field buses or communication buses are also modeled. Those are typical. In this case, they are both CAN buses, and the black box device is also modeled using a separate model. So the entire electronics is modeled as such. So all of them can be connected to each other, and the sensor delays and the actuation delays are then included in your model. And as such, EPSim determines or can determine that the send command, the cut command, needs to be sent at 5 degrees in the loom cycle. So if the weft yarn needs to be cut at 20 degrees, then EPSim tells you that the command needs to be sent at 5 degrees. And EPSim is also able to include the stochastic effects of your embedded platform, as shown over here with those Gaussian distributions in the graph. So what are the key takeaways of this presentation? What do you need to remember? You need to remember that EPSim allows you to model an embedded platform, that it enables you to co-simulate the embedded platform with your control logic, with your control algorithms, that you can evaluate the impact of the time delays on the overall behavior of the system. And as such, it enables you to do that in the nearer stages of your design process, so it enables you to reduce the overall design time. If you need more information or you have questions, then you can ask them in the Q&A, or if you have an interesting case study for us, then you can always contact me using the details below. Thank you very much for your attention.